Carbon ceramic resistor. A material with resistivity ρ is formed into a cylinder of length L and outer radius R outer. A cylindrical core with radius R inner is removed from the axis of this cylinder and filled with a conducting material, which is attached to a wire. The outer surface of the cylinder is coated with a conducting material and attached to another wire. Part A. If the second wire has potential V, which is the outer wire, greater than the first wire, in what direction does the local electric field point inside of this cylinder? So the outer one is at a higher potential with respect to the inner one, the inner conductor, and there's the outer conductor. Now you can see that if I look at this from the top view, the outer one is at a higher potential with respect to the inner one, which means these are positive, these are negative. Negative electrodes, positive electrode is here, negative electrode is here. The electric field must point from the higher potential towards the lower potential. So electric field points from high potential towards low potential, and therefore the direction is radially inward. The electric field must point radially inward from the high potential to the low potential, from the outside coating to the conductor inside. Part B, the magnitude of this electric field is C divided by R, where C is a constant and R is the distance from the axis of the cylinder. Use the relationship potential is equal to integral E dot dl path integral to determine the constant C. Okay, now the electric field is given as minus C over constant C over radial distance R from the center R hat. It is in minus R hat direction because I define the radially outward direction as R hat. The potential difference delta V between the outer cylinder and the outer conductor and inner conductor, V outer minus V inner, potential of the coating with respect to the core is minus the integral from R inner to R outer. We're going from the inner conductor to the outer conductor, E dot dl, the path integral. So this is minus the integral from R inner to R outer. The electric field is minus C over R hat, and I'm moving in the direction of R hat, so dl is dr R hat for this path integral. And this potential difference is V. So these minus signs will disappear. And the integral of C over R dr, because R hat dot R hat is 1, is C natural logarithm of R, which will be evaluated between R inner and R outer. So I find that this potential difference is C times natural logarithm R outer divided by R inner. That's a property of the logarithm. So from this expression, I can find what C is. C, the constant C, is actually equal to the potential difference V divided by natural logarithm R outer divided by R inner. So that's the answer to part B. Part C, what is the resistance of this device? So you can see the current will flow radially inward from high potential to low potential in the direction of the electric field. So if I look at the top view here, I can see that I have basically this conductor, the core conductor, and the outside conductor. And if I consider a cylindrical shell in between these two, so I'm going to have this cylindrical shell whose resistance I will calculate for current flowing radially inward. The resistance of the total geometry will be integral dr, where dr is the resistance of this cylindrical shell, which is the resistivity rho, length, that is the in the direction of the current, is dr, divided by the perpendicular area the current sees. So what is the area seen by the current? If the current flows radially inward like this, it sees the area, the side surface area of the cylinder, which is 2 pi r multiplied with L. So that's the circumference multiplied by L. So that the total resistance will be the integral from R inner to R outer rho dr divided by 2 pi r L. So when I perform this integral, I consider all such cylindrical shells. I will obtain rho divided by 2 pi L. The integral of dr over r is natural logarithm r outer divided by r inner. So this will be the answer to part C. Okay, now part D. A 1 centimeter long hollow cylindrical resistor has an inner radius of 1.5 millimeter and an outer radius of 3 millimeter. The material is a blend of powdered carbon and ceramic whose resistivity rho may be altered by changing the amount of carbon. If this device should have a resistance of 6.8 kilo ohms, what value of the resistivity rho should be selected? The given values are here. L equals 1 centimeter, R inner 1.5 millimeter, outer 3 millimeter. R outer, R inner ratio is 2. Resistance we're after is 6.8 kilo ohms. So the resistivity rho we're looking for, according to the answer from part C, is 2 pi LR, 2 pi capital L, capital R, divided by natural logarithm R outer divided by R inner, R outer to R inner ratio. So this is what we're supposed to calculate for the resistivity, given that we are after 6.8 kilo ohms. So 2 pi, length is 1 × 10⁻²⁰ meters. The resistance is 6,800 ohms divided by natural logarithm of the ratio R outer to R inner 2. This gives us a resistivity of 616 ohm meters. So that's the answer to part So in this problem, we talked about a carbon ceramic resistor that's in the form of a cylinder with length L. The inner core is removed. The radius of the inner core is R inner. It's filled with a conductor, and the outside of this uh, cylinder is also coated with a conductor. The potential of so in between them we have basically um, a material with resistivity rho, which then becomes a carbon, basically carbon ceramic mixture. So we see that when the outside conductor is at a higher potential, the electric field must point from the outer conductor towards the inner conductor radially inward. That's the answer to part A. Knowing that this electric field will be a constant C divided by radial distance R from the center of the central axis of the cylinder, the potential difference between outer and inner conductors, V outer minus V inner, is minus the integral from R inner to R outer, the path integral E dot dl. Electric field is minus C over R hat. dl vector here is dr in R hat direction. If I take the dot product, r hat dot r hat is 1, so minus signs cancel. I find c natural logarithm r for the integral of dr over r, so I get this answer for the electric field, for the potential difference delta v, and c is then v divided by natural logarithm of the ratio of the outer radius to inner radius. What is the resistance of this device? Well, since current does not flow along the axis of the cylinder, but rather the current flows radially inward following this electric field line, the area it sees for a cylindrical shell with radius r here will be 2 pi r multiplied by L, the side as the surface area of that cylindrical region, and it's going to have basically a thickness dr here, so that's the length in the rho L over A formula, dr in minus r hat direction, that's the direction of the current. So we have rho dr over 2 pi rl integrated from r inner to r outer, considering all such cylindrical shells. To get the total resistance, we find rho over 2 pi l natural logarithm r outer over r inner. In fact, we can take rho from this expression isolated. 2 pi rl divided by the natural logarithm of this ratio gives us resistivity. Plugging in some numbers, we can see that we are after a certain resistivity value to get the proper resistance for this carbon ceramic resistor. So we choose the combination of the materials, powdered carbon and ceramic, such that we will obtain this resistivity to get this resistance value.